Today we're starting our next unit that is all about logic and reasoning and proving things. And we're going to start off with going over something called inductive reasoning. And inductive reasoning is when you find a pattern in certain cases and then you try to make a rule based on that pattern. You try to apply that pattern to other things. Geometry and really all of math and all of science is all about, or started with, recognizing patterns that people saw. So they recognize the patterns, they realize this happens over and over again, and so then they were able to come up with rules or guidelines based on those patterns. So that's where all of this stuff came from. So that's why it's very important that we go over it now. So let's look at example 1, and we're just recognizing patterns and trying to use that to predict what will happen next. So for 1A, we want to find the next figure in this sequence. And you can see we've got, for figure 1, we've got 2 pieces. For figure 2, we've got 4 pieces. For figure 3, we've got 6 pieces. So for figure 4, how many pieces should we have? Well, we had 2, then 4, then 6. So we are most likely going to have 8 pieces for figure 4. You could also say that it's the figure number times 2, because figure 1 times 2 is 2. Figure 2 times 2 is 4. Figure 3 times 2 is 6. So figure 4 times 2 is 8. So that tells us how many pieces there are based on this pattern, but which one gets shaded each time? In the first figure, it's the one on the top. In the second figure, it's the one that is on the top left. In figure 3, now that we have 6 pieces, it's on the top and it's on the far left, but it's not this one. It's not the one at the very top. So for figure 4, we could say it's the top and it's on the left, so that would be this one right here. And so let's shade that piece in, because that's what we think the next figure is going to look like. For B, we've got another pattern, this one with numbers instead of shapes and drawings. So we want to look and see how we get from one number to the next one. Okay, and there could be more than one way this happens, so we would have to pick a way and then try it out. So to get from -7 to -21, we could subtract 14. But then if we subtract 14 again, that won't get us to -63. So that's probably not what we're doing. Another way to get from -7 to -21 is to multiply by 3. And if we multiply -21 times 3, we get -63. If we multiply -63 times 3, we get -189. So if we multiply that by 3, what do we get? And we get -567. So that's what we think the next term is going to be. And both of those in example 1 are examples of our conjectures. A conjecture is an unproven statement based on observations, and it's about what we think will happen. And one way to build a conjecture is to set up a table so that we can try to see the number patterns that are going on. So given 5 collinear points, make a conjecture about the number ways to connect different pairs of points. So basically, if we have 5 points that are in a straight line, all on one line, how many different line segments could we draw is essentially what we're asking there. Now, we could go through and figure that out, and we will at the end, But let's see if we can make a guess by looking at how many we could make with 1 through 4, because those are a little easier. If we have 1 point, first of all, it can't be collinear because you need 3 points to be collinear. But there are 0 connections, 0 line segments that could be made. If we have 2 points, still really not collinear because you can draw a line through any 2 points. But we could draw a 1 line segment there. If we have 3 points, we could draw a line segment from the first one to the second one to the third one, or 1 long line segment that goes from the first to the third one. So that would be 3 segments. And then if we have 4 collinear points, we could do the first to the second to the third to the fourth. We could do the first to the third. We could do the second to the fourth. And then we could also do 1 long segment that goes across all of those. And it's kind of hard to see. We should have been counting as we went. But we have 6 segments total. So without drawing them all, let's make a conjecture about how many there will be with 5 points. So how do we get from 0 to 1? Well, one thing we could do is add 1. But we didn't add 1 each time, so we know that's not the pattern. How do we get from 1 to 3? Well, we could add 2, or we could multiply by 3. We didn't do any multiplying with the first one, so we know that's not it. How do we get from 3 to 6? Well, we could add 3 or we could multiply by 2. Again, we couldn't do any multiplying at the beginning, so that's probably not it. So we added 1, then we added 2, then we added 3. What do you think you might add to get the next one? A good conjecture would be that we would add 4, and so we would have 10 line segments we could draw. Let's try to test this out. Now I'm going to make these curves instead of straight, just so they don't all overlap and we can see them a little bit. So we could do first to second, second to third, third to fourth, fourth to fifth. That's 4. We could do first to third, second to fourth, or third to fifth. That gives us 3 more, so now we're at 7. We could do first to fourth and second to fifth. That gets us up to 9. Or we could do the whole thing first to fifth, which gives us 10, which is exactly what we conjectured the answer would be. Now that we have proven that that's what it is, it's no longer a conjecture. It has been proven. Now, sometimes making a table is not very beneficial. So for B, we're still going to make a conjecture. We want the sum of any 3 consecutive integers. Consecutive means in a row. So like 3, 4, 5 are consecutive integers because they are in a row. Remember, integers are no decimals, no fractions, and they could be negative or positive. So let's give our integers a way, let's give us a way to identify them. So our first integer, we're going to just call it n. N is something we use pretty commonly to represent a number. Our second one, since it has to be in a row, will be n plus 1 because it's the next number. And then our third one will be n plus 2 because it's n plus 1 more. So if we wanted to make a guess about these consecutive integers, let's pick some integers out. We've already mentioned 3, 4, and 5. So 3 plus 4 plus 5 is going to be 12. 17 plus 18 plus 19, that'll give us 54. 1,000 plus 1,001 plus 1,002 will give us 3,003. So there's a couple examples, and all of those fit our description. We're adding 3 consecutive integers. And let's look at what our results are each time. What do you notice about each of these? Now, something I noticed that you may not, just because you aren't used to doing this yet, that each of these is 3 times the middle number. I'm just going to use the number symbol. By the way, that's called an octothorpe. So now we've got our conjecture that the sum of them is 3 times the number in the middle. So let's actually use our n's and see if we can prove this is true. Okay, n plus n plus 1 plus n plus 2. When we combine our like terms, that's going to give us 3n plus 3. Now think back to Algebra 1. You could take a GCF out. So we could take a 3 out, and what is left, n plus 1, well, that was our middle number. So we proved using algebra that our conjecture was right. Most of the time you won't have to be doing the proofs right now. We'll get to that. This was just about making an educated guess. Now, conjectures can be true or false. They don't have a truth value when you make them until you try to prove them. So I could make the conjecture that if you study for your test, you will fail. Okay? My conjecture is that you'll fail. Hopefully that doesn't happen. And if you've studied, I can almost guarantee that that won't happen. But it is a conjecture, even if it turns out to be false. To prove that a conjecture is true, you have to prove that it's true every time. So like in this example we just did, because we used algebra to show that it always works no matter what n is, we proved our conjecture. Now, to prove it is false, you need to find one situation where it doesn't work. And we call that a counterexample. One counterexample proves a whole conjecture is false. That's all it takes. A student makes the following conjecture: the sum of 2 numbers is always greater than the larger number. Provide a counterexample to prove this conjecture is false. So we want to add 2 numbers together. And we want the sum, because we're trying to prove this is false, to be smaller than the larger number. The conjecture was that the sum will always be bigger. So for our counterexample, we want the sum to be the opposite of that, smaller. So let's pick some random numbers. 2 and 7. Okay, that would give us 9. And 7 is not less than 9. So that doesn't work as a counterexample. -3 plus -8. That will give us -11. So our sum, -11, is less than, the larger of those two is -3. Is -11 less than -3? It is. So that works as a counterexample. And that we only need one, so we're really done. But just to show you, we could have not 2, we already used a 2. Let's just try -5 and 18. If we added those two together, we'd get +13. And there our sum is let's see here. The greater number would be 18. Is 13 less than 18? Yes, so that would work as a counterexample. So basically, anytime you have a negative number, this is going to be proven false, because negative numbers reduce the sum. So all we need is one situation where we added two numbers together but got a sum smaller than our larger number. For B, a student makes the following conjecture: the value of x squared is always greater than x. Provide a counterexample to prove this is false. So we want to square a number, but we want, because this says x squared is greater than x, we want to have a situation where x squared is less than x. So let's pick a number. Let's just start with something simple. 2. 2 squared is 4. Is 4 less than 2? No. Let's try a negative number. Negative 4, let's go with 5. Negative 5. Okay, when we square that, we get 25. Is 25 less than negative 5? No, so that doesn't work. So we tried positives, we tried negatives. What other numbers are there? What other types of numbers have you run into in the past? And I'll give you a hint. You hate these most likely. Let's try a fraction, because this does not tell us that it's an integer to where we wouldn't have fractions. So let's try 1/3. Okay, if we square 1/3, we will get 1/9, because you square the top, you square the bottom, and 1/9 is less than 1/3. So this works as our counterexample. So when you are using patterns to make guesses, you're using inductive reasoning, and you're coming up with a conjecture. That conjecture could be proven true if you can prove it always works, or it can be proven false if you have one single counterexample. So make sure you fill out your Google form, and make sure you get ready to do those practice problems in class. Good luck.